what I would like to do is just summarize some of the material that we've been doing about the Ice Age floods, just to give you a little clearer picture of some of their key features, not all, just a little bit of points of emphasis and clarification for you. The general layout of glacial Lake Missoula was that it extended over vast areas upstream of where it was being blocked many times, over 100 times, by the Purcell lobe of the continental glaciers coming out of Canada. Would extend down and it would block the exit of the water from the Clark Fork River, basically, that would flow through here. And so it would back up upwards of a couple of thousand feet. And then when this ice dam eventually would be floated by all of this water behind it, it would float, it would fail, and you'd have this enormous release of water, many times, maybe 10 times more than the combined flow of all the world's rivers has been estimated, kind of an amazing number. So when you have that release, you would see if you were to look upstream later, there would be these enormous ripple marks in this area here where the water would flow through, where again the ice dam failure would be about right here. So there would be these Camas Prairie ripple marks, which look something like this. And the basic physics of that is that the higher the velocity of water flow, the greater the distance between each crest of these ripples. And another thing that you would see as a result of these enormous floods would be that in some cases they would be enormous icebergs, and some of them would have had entrained in them or embedded in them large rocks from their origin points way out in Montana. And so the geology there is very different from the geology of, say, eastern Washington. And so what can happen is you could find rocks in places where geologically they could not have formed. In fact, closer to home for a lot of you is McMinnville. There's actually a park where they show erratics there. Again, rocks that are in places where they don't belong. And just to kind of point out that definition a little bit for you. Erratic, boulder found in a place that it could not have formed in. And then the next set of things I want to focus on a little bit is that what happened in environments where there was either slow moving water or very rapid erosive high velocity water. We've already seen the high velocity water carving out areas right in where the lake flowed out, and then in any other areas where there's lots of flow, high velocity flows. So the Wallula Gap was in one of our documentaries, and the whole Columbia River Gorge would be examples of this. And of course, in these areas, when you got water moving many dozens of miles an hour, you're going to have erosion. But then there are enormous areas of deposition. And the way that works, if you just think about it a little bit, and here's an example of deposition. In other words, there's layer after layer after layer after layer after layer after layer of deposits being set down. These are smaller particles. They're not enormous erratics, okay? So what happens is kind of like a bathtub. Let's say that, when you were a kid, you got really muddy and your mom said, now you go get in the bathtub now. So you get in there and you're covered with mud. And you get in there and there's all this murky water, right? And if you're swirling it around, it kind of stays entrained in the flows. But then if you let the water stop moving and you just sit there, a lot of it, what does it do? It settles to the bottom, doesn't it, right? So the higher the velocity of flow won't allow for the deposition of small particles. But as the water slows down, more and more gets deposited. So what happened was there were places where there would be a dam and it would block a lot of water from flowing through it. So areas behind that would back up, and what they would look like is something like what you see on this map, where here's the discharge of the floods, right? And so they come rushing through the Wallula Gap, but the Wallula Gap can't possibly handle all that water. So a lot of it just backs up, and some of it backs way up into these areas like Walla Walla, and even further back into these areas here, where basically you have very slow water. It's kind of like a big pond there. so it can deposit out those sediments. So every time you have a new flood event, you'll get a backup of water and a new deposit of sediments here. And so those sediments look like this, or like there to the left, or there. Really, really beautiful, okay? And so just a little bit about the depositional environments, okay? I hope that that helps us kind of understand this. Let's look at this in another way too on a map, if we may, just for a bit. This would be the environment as we think of it today, and this would be where the Purcell lobe came down, and then this is the whole backup through the Clark Fork River drainage today, moving into western Montana. And so this is, you know, an enormously large area. So then one of the kind of fun things is that the Purcell lobe, as it would come down here, carved out this lake. This is in your notes. It's 1,000 feet deep in some of the deeper areas. And in fact, there was a big lobe at the end of the glacier. Sometimes when it reached this far down, made this giant moraine, a terminal moraine, which is just a big pile of gravel and boulders and stuff, where the glacier would push south, push, push, push. So it came here and it blocked off this area to some degree, and it blocked off the St. Mary's River, or St. Joe River, excuse me, the St. Joe River, and it literally blocked it and made a barrier there for it. So instead of it flowing through its valley, it backs up as a lake. That lake still survives today. This is Coeur d'Alene Lake. And in fact, the very last slide in my presentation of general landforms is Coeur d'Alene Lake, formed in this manner. So you have these huge floods come through here, through the Spokane Valley, and then they go out over these channeled scablands areas, which you saw in the Oregon Field Guide. Really excellent work. And of course, then this is what we saw before, but now on a more detailed map, where you'd have the Wallula Gap, and then all the backwater flows out into some of these areas. So I hope that helps.